Okay, in our previous videos, we discussed open set and closed sets in a topological space. In this video, we going to study interior of a set using open set and closure of a set using closed sets in a topological space. Let me give you the formal definition and then I will give you some examples of interior and also closure of a set in a topological space. So here is the formal definition. Let's say X is a topological space. X is a topological space and A is a subset. A is a subset of this topological space X. Then let me first define the interior and then I will define the closure of the set A. Then the interior of A, which is denoted by interior of A, which is denoted by int of A. This is how we denote the interior of a set, int A. Interior of A. Then the interior of A denoted by this symbol is defined as defined as the union of all open sets is defined as the union of all open sets contained in A. Okay. Alright, so this is the definition of interior of a set. So you can see in this definition, let's say A is a subset of a topological space X, then the interior of A is denoted by int A and is defined as the union of all the open set contained in A. So basically, to find the interior of the set A, what we need to do is we need to find all the open set which are the subset of A. Then we need to take the union of those open sets which are contained in A. Since the interior of A is the union of the open set which are the subset of A, so we can say that you can write down as a note, since the interior of A is an open set as being the union of all the open set. In topological space, union of all the open set is open. So we can say that interior of A is open. Okay, interior of A is open, and also you can see here interior of A is the union of all the open set which are contained in A. So that we can say that this interior is the largest open set contained in A, because it is the union of all the open set contained in A. Since each set they are the subset of A and they are also open and their union is open, that's why interior is open, and each open set is a subset of A. So when you take their union, that's gonna be the largest open set which is largest open set which contained in A, or is the largest open set which is the subset of the set A. So I'm just writing as a note, interior of A is open as being the union of open set, and then also it is interior of A is open, and the largest open set contained in A. Okay, so these are the property of interior of a set. I will give you example in a few minutes. Before that, let me first define the closure of this set A. Again, we have X, a topological space. A is a subset of X. Then the closure of A, which is denoted by A bar, and is defined is the intersection of all closed sets containing A. So this is the formal definition of closure of a set A. Closure of a set A, which we denoted by A bar, and is defined is the intersection of all the closed set containing A. So in order to find the closure of a given set, what you need to do, we need to find all the closed set we need to find all the closed set such that A is a subset of each closed set, and then we take their intersection. And we know that in topological space, the arbitrary intersection of closed set is closed. So A bar, or closure of A, is closed, is being the intersection of closed set. And also, since A closure is the intersection of the closed set, or intersection of all the closed set, such that A is the subset of each one, so we can say that intersection is the smallest closed set, such that A is the subset of that set. Or we can say that closure is the smallest closed set containing A. Just let me write down this property as a note. The first one is A closure is closed, is a closed set, and the smallest closed is the smallest closed set containing A. So these are the two properties of closure we have here. It is closed as being the intersection of closed set, and is the smallest one because this is the intersection of all the set containing A. Now let me give you some example of closure of a set, and then also interior of a set in topological space. Let me begin with the example of closure. Let me give you the example of closure of a set. Then after that, I'll give you the example of interior as well. Let's say X is a set or is a topological space whose elements are A, B, C, D, and E with topology tau, whose elements are empty set in the whole set X, and then this singleton set A, and then C, D, and then this 3 element set A, C, D, and then 4 element set B, C, D, E. Okay, so here we have the set X with this topology, and the elements of the topology are listed here. Now in this example, let me call this is the example number 1, and in part A, we're going to find the closure of this singleton set. So obviously this singleton set B is a subset of X, and we want to find the closure of this one. And then also AC is obviously this is a subset of this set X, and we want to find the closure of this guy. And also here BD, it's obviously that is the subset of X, and we want to find the closure of this guy as well. Okay, now we are going to find the closure of those 3 subset of X under this topological space. Okay, now let's compute the first one. Okay, let's compute the closure of this singleton set. So as I said before, in order to find the closure of any set, the first thing what we need to do is we need to find all the closed set in X which contains this set. Okay, and after that we going to take their intersection. Okay, first of all, let's list all the closed set in X under this topology tau. So the closed sets or closed subsets of X are, so obviously the empty set is both closed and open, and the whole set X is both closed and open. So the closed subsets of X are empty set and also the whole set X. Now to find the next closed set, let's take a look on the open set. So under this topology tau, so this is our open set, and if you take the complement of open sets, that's gonna be closed set. And also if you take the complement of the closed set, that's gonna be open set. So the intersection of complement of A, that's gonna be our closed set because it is open. Okay, and the complement of A in the set X or in the topological space X, that's gonna be, so you delete A from this set X, so it's gonna be B, C, D and E. So that is my next closed set. And similarly, when you take the complement of this set, since it is open, if you take the complement of this guy, that's gonna be closed. So complement of CD in the set X, that's gonna be just you remove C and D from the set X, then the resulting set is A, B, E. And then we take the complement of that guy. So the complement of this one is gonna be B and E. And then finally we take the complement of B, C, D and E, and which is going to be A. So these are the list of all the closed set of X under this topology. Okay, now let's find out the closure of this singleton set B. To find the closure, first thing what you need to find the closed set containing this set. Now you can see here phi is the empty set. I mean these are the closed set. So we need to first find all the closed set containing this set. Since phi is an empty set, so it is obviously this is not this set, this singleton set B is not contained in this empty set. or is not the subset of this empty set. And obviously X, X contains this guy, or the singleton set B is contained in X. So X is a closed set containing this set, and then also B, C, D, since we have B here, so this set is B, C, D. This is also a closed set containing B, and then so we take their intersection. And also we have here this set A, B, E also also this guy B is containing here, and then also the other one B, E is a closed set such that this singleton is a subset of this one, and there is one more closed set A, but this one is not the this singleton is not the subset of this one. So this closed set, we don't need that one. Now if we take their intersection, then it's gonna be, you can see BE is everywhere, so the closure of this singleton set is BE. So that is how we can find the closure of a set in the given topological space. First you find all the closed set containing the set, that's the given set, and then you take their intersection. Okay. Okay, let's also compute the closure of this two element set. So in order to find the closure of this two element set, we need to find the closed set containing AC. Now empty set is closed set, so but is empty set does not contain this guy, and the whole set X, obviously it contains AC, and B, C, D, this is the next closed set B, C, D, E. It doesn't have A, so it does not contain AC, so we don't need this guy. A, B, E, it doesn't have C, so this A, B, C does not contain AC, so we don't need this one. And also B, E, there is no A, so it does not contain, or AC is not the subset of B, E. And then the last one is, obviously this is one element set, but AC is two elements, so we don't need that one. So that means the closure of AC is the whole set X. Okay, and then the final one, similarly, we can compute the closure of BD. So if you compute the closure of BD, that's gonna be this set B, C, D, E. Okay, so I'm just writing similarly, but if you want, you can work on this one, like I did in the first two parts. So from here we can say that the smallest closed set containing BD in this example is this set. Okay, and then also the smallest closed set containing this set AC is X, the whole set, and the smallest closed set containing the singleton set B is BE. So this is how we can find the closure of the given set in a topological space. Alright, so part B, let's find out the interior of a set in X. Let's say this BCD, this is a set, obviously this is a subset of X, and we want to find the interior of this guy. Okay, so let's find out the interior of this set A. So what is the interior of this set A? So in order to find the interior of the given set, what you need to do is you need to find all the open sets in the given topological space under the given topology, such that each open set is a subset of this guy, and then you take their union. Okay, let's take a look in our example. So this is our set ABCD. So sorry, not ABCD, it's just BCD, whose elements are BCD. And to find the interior of this one, now I need to find each open set in X, which is the subset of this guy. Now let's take a look. these are the open set. I mean, each element in the topology, that's going to be open set. Now, since empty set is obviously the subset of any set, so interior A, we need to first find all the open set such that each open set is a subset of that guy, and then we going to take their union. Empty set is the subset of any set, so we need that one. Now let's see next one. This one, the next one is the next open set is A, and let's see whether this is the subset of given set or not. Obviously this is not the subset of given set because there is no A, so we don't need that guy. And the next one is CD, that's the next open set, and this is obviously the subset of this one, so we need that guy CD, and then we take their union because we need to take the union of all the open set such that each open set is the subset of this set. Next one I have ACD, but is not the subset of this one because there is B, there is D, no, there is A, but A is not the element of this one. And then similarly you can take the other one, as obviously that is not, because here you have E, but here you don't have E. So that means there are only two open set in the given topological space such that they are subset of A. Now we take their union. Once we take their union, then it's gonna be CD. So this is the interior of this set A in the given topological space, and we can say that this is the largest open set in X containing A. This is the largest open set in X such that this open set contained in A. Okay. Alright, so here we defined interior of a set and closure of a set, and then I gave you a few examples. Now there is another way of defining interior of a given set in a topological space. Now let me give you another definition or another way of defining the interior of a set in a given topological space. X is a topological space. Let's say X is a topological space. We have X is a topological space, and A is a subset. A is a subset of this topological space X. First we're going to define the interior point of A, and then using interior point of A we're going to define the interior of A. A point, let's say lowercase a of A is, it's called an interior point. It's called an interior point. It's called an interior point of A if there is an open set, if there is an open set B such that element A is in B and B is a subset of A. This lowercase a is an element of the subset A. This element is called the interior, is called an interior point of the set A if we can find the open set B in X such that this element is in this open set and that open set is the subset of A. Then we call A is an interior of the given set. This lowercase a is the interior of the given set A. And if we take the collection of all those interior points, then that is called the interior of the set A. Okay. Then the set of all interior points of A is called the interior of A, and we have already learned the notation for interior of A, which is denoted by INTA. Okay, now let me give you example of interior point and then interior of a set. Example, let's call is the example number 2. Like in this example number 1, let me take the same set whose elements are A, B, C, D, and E. This is a topological space with topology tau. Obviously, we need empty set, the whole set, and then let's take this is another element in the topology, and this is another open set in X, and then A, C, D, and then I have B, C, D, E. So this is our topology on the set X, or on this topological space X. Now here let's say A whose elements are B, C, and D. Obviously this is a subset of X. Now here find interior points of A and also the interior of A. Okay, now here we're going to find the interior points of A and then interior of A. Solution. So interior points means what? Any point of this set A, which is called the interior point of A, if there is another open set such that that point is in that open set and that open set is a subset of A. Now let's say this A has B, C, D, 3 elements. Let's see whether C is the interior point or not. This guy C. Obviously here C is in A. That's the first condition we need, right? C is in the set A. And then also if this C is an interior point of A, then there should be an open set containing C, and that open set is a subset of A. Open set of X under this topology tau, these are the open set. Here is the list. Now this C is in this set, right? And this is also subset of A. That means C is the interior point of A. And now you can see here C is obviously in the whole set X, but X is not the subset of A. So this is not the open set that we need here. We need the open set containing C such that that open set is a subset of A. Since we have such a open set containing C and that open set is subset of A, so C is the interior point of A. So we can say that C is an interior point. C is an interior point of A because C is in that C is in this open set CD, and which is subset of A. And also we can check D is an interior point of A because there is an open set. We can say this is the same open set contains D, and then this open set is subset of A. So also we can say that also D is an interior point since D is in the same open set CD and CD is subset of A. It doesn't have to be the same. All we need an open set containing D, and that open set is a subset of A. So far we found that C and D both are the interior point of A. Now let's see whether B is the interior point of A or not. And here B is not the interior point, because if B is the interior point, then there should be at least one open set containing B, and that open set it has to be subset of A. Now you can see here B, these are the possible open set containing B. So B is in obviously in X, but X is not in this. X is not the subset of A, so this X doesn't work, and it doesn't have B. So obviously B is not an element of this one, so this open set doesn't work. And also CD is open, but it doesn't have B, so this one it doesn't work. And only the open set that has B is this one, B, C, D, E. But B, C, D, E, this set is not the open subset of A, because this is not the subset of A because it has E. A doesn't have E. So we can conclude that B is not an interior point. B is not an interior point of A. This is because there is no open set. There is no open set that contains B. There is no open set that contains B and contained in A. Okay, that's why B is not the interior point. So this set A has only two interior points, which are C and D. So in the second part we have to compute the interior of A. So thus we can say that interior of A, if you want you can use the parentheses, or we haven't used the parentheses, thus let me write down interior of A, that is the set of two elements which are C and D. So this is how also you can compute the interior of given set. Okay, that's the interior of A. And if you go back to the example number 1, we have already computed the interior of this set BCD. Let me show you here. BCD, we have taken the same set X, same topological space X, same topology, and then we have computed the interior of A, which we have found CD using those open set, and also here using the interior point we got the same interior of A. So that doesn't matter which definition you use, you're going to get the same answer. Okay, so this is another example of interior of set in the topological space. Okay, now let me give you one more example. Example number 3. Example number 3, interior. Example of an interior. Okay, interior of a set in given topological space. Let's say my topological space X is a real line with a standard topology, with a standard or order topology, order topology, standard topology and order topology, these are the same thing. So here the basis elements are open intervals, okay, or open sets are open intervals or their union. Okay, now let's say the set A is Q. Q is the set of rational numbers, set of rational numbers. So there is a standard notation for the set of rational number, which is Q. All right, now here interior points. Let's find out the interior points of set of real number. Set of rational number. We have this real number here, and then our set is the set of rational number. Okay, and let's say this R is a rational number, and if this R, this R is a rational number. Here we are taking R is a rational number, and if this R is an interior point, then what you have to have is we should be able to find an open set in R with the standard topology, and in standard topology, open sets of R, they are like simply the open interval. Okay, then you should be able to find an open interval containing this real number, and then that open interval, it has to be a subset of rational number. Now it is possible to find the open interval containing R, but any open interval containing R, it also contains the irrational number, so that this open interval is not going to be a subset of Q. Okay, so here let's R is a rational number, and if it is an interior point of Q, then by definition, by this later definition, we should be able to find the open set in R with the standard topology, and the open set in the standard topology, these are like the open interval. It is possible to find the open interval containing this real number R, but that open interval, it contains the real number. At the same time, it also contains the rational number. At the same time, it also contains irrational number. And if the open interval contains irrational number, then we cannot say this open interval is a subset of Q. That means R is not the interior point of Q. Since R is the arbitrary rational number we took here, that means any rational number is not the interior point of Q, which means interior of Q, if there is no interior point of Q, that means the interior of Q, that's gonna be an empty set. Okay, since every open set, which are basically the open interval, every open set of R contains both rational and irrational numbers. There are no interior points. There are no interior points of the set of real number Q. If there are no interior point of the set of real number Q, then so we can say that the interior of Q is empty set. Okay, because there is no interior point of Q, so the interior of Q is the empty set. This is another example, and it's kind of a very popular example. All right, now I'm gonna give you a lemma without proof. That lemma gives us a relation between open set and the interior of open set, and also the closed set, and then closure of that set. So in fact, we can use this lemma that I'm gonna give you. We can use this lemma to check whether the given set is open or not, and also whether the given set is closed or not in a topological space. Okay, lemma. Let's say X is a topological space. X is a topological space, and A is a subset of X. Then this subset A is open if and only if interior of A is A. Okay, if the given set A is open if and only if interior of this set is itself. So here it says if and only if, that means two-side implication. Two-side implication means if A is open set, then the interior of this set is going to be same as itself, and also if interior of a set is the set itself, then we can say A is open. Okay. Similarly, A is closed, or let me write down, and A is closed if and only if closure of A is same as A. So like I said earlier, I'm not going to give you proof of this lemma here, but if you are interested in proof, you can take a look in Monker's book. But this lemma is very useful to check whether the given set is closed or not, and also whether the given set is open or not. If given set is open, then you can say interior of that set is same as itself, and if the interior of set A is itself, then we can say that that set is open. And similarly, a set is closed if its closure is same as the set itself, and if the closure of the if the closure of a set is itself, then that set is closed. So using this lemma, we can say that here this Q, or the set of rational number, is not open, because if it is open, then interior of this guy, it has to be Q, but this is not. But the interior of Q is empty set, so Q is not open set. Okay. All right. Now here, next I'm going to give you one more definition, and which is kind of very useful definition. And I'm sure you guys have seen this definition in a real analysis course. Okay, let's say X is a topological space, but here we are going to define in the context of topology. Let's say X is a topological space. In open set U in X is a neighborhood is an open set U in X is a neighborhood of an element X in X if X is also the element of U. Then this open set is called the neighborhood of this element X. Let's say X is a topological space, and this lowercase x is an element of X. Then the open set in X is called the neighborhood of this X if the X itself is an element of U. then this x is called the, sorry, u is called the neighborhood of x. So we have like this. Let's say this is a big set x, and we have a point x, or let's say the element of x, and let's say this is our u. Since u is open in x, if and also u contains x, so u is the neighborhood. But let's say I have another open set here, u1. We cannot say u1 is the open set. Sorry, u1 is a neighborhood of x, because x is not in u1. So this is it looks as a pretty simple definition of neighborhood of a point in a topological space. Let me give you example of neighborhood of a point in topological space. Example, I think it is example, let's see, example number 4. This one is example number 4. Okay, let's say my set X is, or my topological space is A, B, C, D, and E, with the topology, tau, empty set, whole set, A. I'm working on the same example that we work in number 1, and I guess it was also in number 2. A, C, D, and then we have A, B, C, D. This is the topology. Oh no, not. It looks like this is not the same example or same topology. We are taking the different one, A, B, and E. So we have this topological space with this topology. Alright, now here C, you can see that this element C is an element of X. Let's find out the neighborhood of this C in this topological space under this topology. So by definition, any subset of X that contains C, any open subset of X that contains C is a neighborhood of C. Now you can see these are the open set. Empty set doesn't contain C, so empty set is not neighborhood of C. And X is open set and also contains C, so X is a neighborhood of C. This open set is not, because it doesn't contain C, and this one is not as well. And ACD is a neighborhood of C because it contains C, and ABCD also a neighborhood of this point C because it contains C, but the last one is not. So it looks like there are 3 neighborhood of C here. Okay, so the neighborhoods of C are those 3 sets, 3 open sets, right? A, B, C, D, A, B, C, D, A, C, D, A, B, C, D, and the whole set X. Alright, so you can see from here, for any point in the given topological space, the topological space itself is a neighborhood, because topological space is open set, and also obviously it contains its element. Okay. All right. Now I'm going to give you one more theorem here, and then example related to this theorem. And this the theorem without proof. This theorem describe closure of a set using neighborhood and also using basis element, okay, of a topological space. Let's say X is a topological space. X is a topological space, and A is a subset. A is a subset of X. Then Then this theorem, it describes closure of a set using the neighborhood and also using the basis element for our topology in this topological space X. Then X, this is an element which is an element of X. Then X is in closure of A if this X, it may or may not be in A. X is in closure of A if and only if every neighborhood of X intersects A. So you have if and only if condition here. That means if this X is an element of X, it may or may not be in A. This X is an element in the closure if and only if every neighborhood of X intersect A. So this is if and only if condition. That means if X is in the closure of A, then every neighborhood of X intersect A. Intersect means if U is the neighborhood of X, intersection of U and A is non-empty set. That's the meaning of intersect. Okay, and also if every neighborhood of X, it says every neighborhood of X. If every neighborhood of X intersect A, or every neighborhood of X, if you take the intersection of every neighborhood of X with A, if that intersection is non-empty, then X is in the closure. Obviously, the set A, every element of the set A, they are in the closure, because we have already seen this relation. A is subset of A closure, and then also interior of A is subset. This relation we have seen in the first definition, because this interior of A, which is the largest open set contained in A, and A closure, that is the smallest closed set containing A. And so since A is the subset of A closure, so any element of A, they are already in A closure. That's why X is in X. It may or may not be in A. Okay, but X is going to be in the closure of A if every neighborhood of X, every neighborhood of X intersect A. And also this X is in A closure if and only if every is we are saying every, so here is a strong condition. Okay, every basis element B containing every basis element B is the basis element for the topology on this topological space X. If and only if every basis element B containing X intersect A. Alright, so here also you have if and only if condition. Okay, as I said before, I'm not going to give you the proof of this theorem. If you are interested in proof, you can look at in Munker's book. But I'm going to give you some example. Let's say this is example number 5 related to this theorem. Okay, let's say X is the set of real number with a standard topology. Okay, standard or order topology. We have the set, our topological space is the set of real number with the standard topology or order topology. That means the basis elements are like the open interval or the union of the open interval, and also the open sets are open interval or their union. Okay, now we want to find, let's say A is the this interval. Okay, Now we want to find the closure of this interval using this theorem. Okay, now you can see, so what we have here is we have this real line, and this is positive infinity, this side is negative infinity. I have 0 and 1 here, and then this is my A. Okay, this is my A. This is my A, and I want to find the closure of this guy. And obviously, closure of this interval, each number or each real number on this interval, they are already in A closure. That means A is in the A closure, and all the real number between 0 and 1, they are in A closure. But we are not sure whether this A is, because this 0 is, we have parenthesis, 0 is not included in this interval. So we are not sure whether 0 is in the closure of this set A or not. If it is in the closure, then what you have to have, every basis element of or every neighborhood of this 0 should intersect it, and that is possible, right? The neighborhood of 0, which means the open set in R containing 0, and open set in R, they are simply the open interval, right? So if you take any open interval containing 0, that takes the point on the left side, and also that takes the point on the right side. So then the point on the right side, they are the intersection of this open set and the set A. So this is the intersection. So that means the intersection of the neighborhood of 0 and A is not empty. That means every neighborhood of 0 intersect A. So 0 is in the closure of A. Okay, so here we can say 0 is in closure of A. But the element of closure, they could be in A or not in A. You can see here 0 is not in A but is in the closure. So far what we have seen is the closure of A contains every point of every real number in A and also the 0. Now let's consider a real number which is outside of, so far we have seen 0, 1 is the closure of A, or this set, every real number of this set in the closure of A. Now let's investigate outside of this interval. Let's take a point somewhere here. Let's say it is -1, and if -1 is in the closure of A, then every neighborhood of 1, that means every open interval containing A, should intersect A, and that is not possible. If you take this open interval here containing -1, that is the neighborhood of -1, it does not intersect A. So here what we can say here is, if you pick any point outside of this interval, then we can find a neighborhood. We can find at least one neighborhood which does not intersect A. So that means outside of this interval, we don't have, or outside of this interval, none of the real number, they're going to be in the closure of A. So the closure of A is simply, this interval 0 to 1, okay, including 0. Okay, let me write down here what I just described. Since every neighborhood of 0 intersects A, so we can say that A is in A closure. Obviously, every element of A, they are also in A closure. And also, every point outside of 0, 1 has a neighborhood disjoint from A. Disjoint means the intersection of a neighborhood and A is empty set. Thus, A closure is 0, 1. Okay. This is an example of the closure of a given set. This 0, 1 in R using this theorem. Let me give you a couple of more examples. Let's call this one is A, and then this one is B. Still we are in the topological space R with the standard topology, but we have different set, which is the set of all 1 over n. N is a natural number. So basically B is this set here. B is the collection of those you can say B is the collection of the reciprocal of natural number. Okay, let's say this is 0 and this side is positive infinity, negative infinity, and so the elements of B, they are all going to be between 0 and 1, because if you take the reciprocal of 1, that's going to be 1. If you take reciprocal of 2, that's going to be 1/2, right? Here reciprocal of 3 is 1/3, and reciprocal of 4 is 1/4. You go closer, and then you are very close to 0. Okay, now here then the closure of B, obviously all those real numbers which I have marked here are the reciprocal of those natural number. They are in B closure because they are the element of B, and also 0 is going to be in the closure, because if we find the neighborhood of 0, which is the open set, so that open set of R or open interval of R containing 0, it goes on the both side of 0, left side and right side, and all the elements of the B, they are in the right side. That means they intersect the right side part. So every neighborhood of 0, no matter so how small or how big neighborhood, or how small or how large open interval of 0 you take here, that open interval intersect the point on the right side. So 0 is also 0 is in closure of B. So the closure of B is gonna be this singleton set 0 and B. Okay. And other real numbers, they are not going to be in the closure of B, because we can, for the remaining real number, we can find at least one neighborhood which is disjoint with B. One more example. Let's say our set is this one is the union of singleton set 0 and this interval 1, 2. So basically we have this one, this is 0, and we have 1 here, let's say 1 and then 2 here. So our set C is this 0 and then union of 1, 2. Now the closure of C, then closure of C is gonna be, obviously the set C is going to be itself. That means 0 and 1 up to 2, that's open interval. Now you can see here those endpoints, they are going to be in the closure of C, because for example if we take any neighborhood of 1, that will intersect the right side of this interval, or right side of 1. So 1 is in the closure, and also by the same reason 2 is also in the closure, and then 0 is also itself an element of C, so it's gonna be in the closure of C. So the closure of C is going to be 0, and then the interval from 1 to 2, including 1 and 2, and the remaining real number, they are not going to be in the closure. So the closure of C is going to be 0 union of this interval 1, 2. Okay, one more example. Let's say let's take this set of rational number. Then the closure of set of rational number is gonna be obviously every rational number is in the closure of Q, and then also the irrational number, they are going to be in the closure of they are also going to be in closure of Q, because if you pick any rational number, we can find the open interval which contains both rational and irrational number. In fact, if you take any real number, doesn't matter it is a rational number or irrational number, and the open interval containing that real number contains both rational and irrational number. So that means, like I said, any rational number is in the closure of Q, and also the irrational number, they are going to be in closure of Q, because any open interval or any neighborhood of that rational number, which is the open interval, contains both rational and irrational number. If that neighborhood of irrational number contains rational number, that means that neighborhood intersect Q. So the closure of Q is going to be the union of Q and irrational number, which is the whole real number. Okay, so the closure of rational number is the set of real number. Okay.